So guys, welcome to the very first lecture of EM 122. It's going to be very, very exciting. And as I said to you in the introduction, you should definitely stay with this and try and make sense of this. This first lecture mainly is about notation and about terminology. And so therefore that's really, really important, because in mathematics, or in engineering mathematics, one of the problems is that people use terminology and use notation, and they don't really define it a lot. And so therefore you need to know what's going on before you can actually start messing about with this stuff. So you need to know the very, very basics. So this is like learning a language, I suppose. You need to know if you're learning German, you need to know the German for man and woman, and this is exactly the same here. So you need to know the notation and the terminology of matrices when you start using matrices. So please just go through this. Stick with this. I know it's terrible and you have to do this, but you should definitely work your way through this. All right. So the first thing I want to talk about is basically what is a matrix. And a matrix is very simple. It's a construct in mathematics. It's just a rectangular array of numbers. That's all it is. It's a rectangular collection of numbers. And that's all a matrix is. Okay, so let's look at some examples here. So if you look at the first, the 1, 2, 3, that's a matrix, because it's a rectangular series of numbers. It's a row, or it's just three numbers written down. No, you note there, folks, there's no commas in between the numbers, and that's traditional when you use matrices. There are no commas, but you see that 1, 2, 3 that has a rectangular structure. Okay, so that is a matrix. If you look at the second example, then that's not rectangular, because there's a gap, right? There's something missing underneath the number 10. Now, if there was a 0 there explicitly, then you would have a matrix. But because there is nothing there, you don't. The number 2 by itself is both a matrix and it's not a matrix. It's a very, very fluid situation. Okay, so a number by itself you can regard as a matrix, but people usually don't. All right, so it's a kind of an exceptional case when you have a single number. You can make the case for the fact that it is a matrix because it's a rectangular array. All right, you could make that case. It's a very simple rectangular array, but you could make the case for it. And sometimes people consider it as a matrix, but most of the time people don't. So let's just accept that numbers by themselves aren't matrices. Okay, let's decide that. If you look at the next collection of numbers, you've got 3, 4, 5, 1, 1, 3, minus 2, 4, 3, 4, 7, 9. That's definitely a rectangular array, or rectangular collection of numbers. So that is a matrix. And then the last example, the one on the right there, where you've just got symbols, the y and the STYB, that's not a matrix, because it's a kind of a cross-shaped geometry, and it doesn't have the rectangular structure. So you just walk away from that. That's not a matrix. And if you have a matrix, guys, traditionally you want to isolate it away from the rest of the world and keep it to yourself. And the way in mathematics, you isolate a matrix from all the other matrices and all the other things that exist in the universe is you put brackets around it. Which brackets is up to you. Really, it really is a personal choice, but there are two conventional choices: square brackets or the round brackets. I will probably use the square brackets. All right. If you want to use the round brackets, or if you want to use the curly brackets, go and knock yourselves out. It doesn't matter. But the square brackets look better, I suppose, or look best. So that's the one that people use. So for the 3 cases above where you have kind of a matrix structure, well, the 2.5 cases, what you should do is you should maybe rewrite the 1, 2, 3 like that. You put the 1, 2, 3 down and you put brackets around it. Now, as I say, the number 2 by itself, I shouldn't really do that, but I'm a rebel. But you shouldn't really. It's not a matrix really. It's kind of in the twilight zone of matrix land, the single numbers. Yeah, I shouldn't really put it down. So you can if you want to, but you shouldn't really. And the last one then is this. It's just a rectangular collection of numbers there. The 4th one there in the series of objects, and I just put square brackets around it. And as I say, square brackets look better than the round brackets, so that's the one that people typically use. Okay, and the reason why you do this, guys, as I say, you want to isolate that matrix from all the other matrices that exist in the universe. Right, now you can there's some kind of structure to matrices, and there's some terminology that you need to know. You can subset a matrix into what are called rows and columns. And if you look at this matrix here, it's 6, 10, 5, 3, 0, 2. If you look at the first horizontal series of numbers, it's just 6 and 10. That's called row 1, or the first row. The horizontal series of numbers 5, 3 is called row 2. And the last one is called 0, 3. So you've got rows here, and you've got also if you do the vertical collections of numbers, you get 6, 5, 0, that's column 1, 10, 3, 2, that's column 2. Now, I've been doing this so long, guys, that this terminology seems kind of obvious to me. I don't know if it's obvious to you. Maybe if you use spreadsheets, is that the same terminology you use? I think it is, isn't it? I think it's exactly the same terminology. And so maybe that might be more, that notation or that terminology is meaningful to you. Certainly, I've been using this so long that I just assume that it is what people use. And it's an intuitive thing, but maybe it's not. But it's a very, very important way of subsetting matrices, of isolating elements in the matrix. Each number in a matrix is called an element. Okay, so each of those 6 numbers is an element of the matrix. Now, in this case, guys, I've used curly brackets for the matrices. For the matrix, it doesn't matter. Now, here's a very, very important little idea. It's called dimension of the matrix. You will see that this matrix here has got 3 rows and 2 columns. And so it's called a 3 by 2 matrix. Or you could say the dimension of the matrix is 3 by 2, but usually we just say it's a 3 by 2 matrix, and the idea, or the noun dimension, is implicit in that statement. Okay, and this is very, very important. And you write down the number of rows first, and then you put an X cross, and then you write down the number of columns. And the reason why you write down the number of rows first is convention. So when they first started inventing this and looking at this stuff, many years ago, they had to come up with some convention. So the convention is you write down the number of rows first, and then you write down the number of columns, and then you put a cross or multiplication sign between them. Now, this is not multiplication, okay, but it's the multiplication sign. So in the context of matrices, 3 by 2 is not 6. It's just saying that there's 3 rows and 2 columns in the matrix that I'm dealing with. So dimension is really, really important in when you start messing about with matrices. It's really, really important, actually. It's a very fundamental concept. Okay, but it's very easy, I think, right? So you just count the number of rows, you count the number of columns. Now, here's where it gets a little bit hairy, I suppose, and I'm going to contradict myself, actually, on this slide as well, which is great. But by convention, again, guys, matrices are usually denoted by capital letters, and in print, boldface capital letters. If you're using a pen and paper, as you might do at home when you're doing some calculations, you write down the capital letter and you put and you underline it. Okay, so you write down, A with a line underneath the A. But in print, for instance, on these slides here, I'm going to use boldfaced. And usually it's a capital letter, but sometimes you use a lowercase letter, and I will talk about that in a second. Now, each element of a matrix is defined by its position. So if you have a matrix which you've called capital A, the element in row I and column J is denoted by lowercase a subscript ij. So this is important. Now, when I first started doing this very many years ago, I just couldn't get my head around this at all. And it is, I remember struggling with this. I struggled with a lot of things when I was a student, but this is one of the things I struggled with. This idea of the notation for elements in a matrix A, but it is actually not that difficult. Maybe it was explained badly, and maybe I'm explaining it badly to you, but hopefully it becomes a little bit clearer. Okay, so the idea is here, guys, you call a matrix by a capital letter, and you call the elements, the numbers within the matrix, by lowercase letters, the corresponding lowercase letter, with subscripts. And the first subscript denotes the row, and the second subscript denotes the column where the element is. Okay, now I suspect that I'm making this much more complicated than it should be, and maybe this is very obvious to you. But as I say, when I was a student with no friends many years ago, I don't know why I said no friends, but it's true. But when I was in this took me a while to get into. Okay, So here's an example. So I've contradicted myself straight away here, guys, because if you look at the very first bullet point there, I said, look, a matrix is usually capital letter with boldface, and I haven't boldfaced this one. Okay, so this just show you that actually sometimes people use different notations for matrices. So just get happy with the fact that that people use different notations. I will try and be consistent and use bold-faced capital letters, but here I've used just a capital letter. Okay, now underneath then you see lowercase a11. So this is read as a11, means the element of the matrix capital A in the first row and the first column, and that element is 2. So a11 is equal to 2. Okay, a12, so it's lowercase a subscript 12, is telling you to go to the matrix A, go to the first row and the second column and read out what the element there is. And in this case, the element there is 4. So a12 is 4. A13 is 5. Okay, it's the first row, third column, that element is 5. A21, so what you do is, again, you go to the second row and the first column and you get 7. A22 is 8, second row, second column. And the last one then, A23, which is the element on the second row and in the third column, is 9. Now, why is row first and column second? It's convention. There's no reason why it should not be the other way. But don't. This is the convention, and it's in use. Everyone just accepts this convention, and it's the same way we use the word dog for a dog. This is exactly the same here. It's just convention. Okay, so row first, column second in terms of subscripts. Now, as I say, guys, this is something that I struggle with, and maybe you might as well. Maybe you won't. Maybe this is just my brain. I just could not get my head around this stuff. But it is what it is. So maybe you should get used to it. It actually is kind of important. And those of you who do programming, and when you do programming, this idea of identifying elements of a matrix is really important, being able to pick out a number, because a matrix in computing is called, when you start programming, a matrix is represented as an array. And usually, sometimes you want to pick out elements in your array, and this is how you do it. Exactly the same way. The first subscript refers to the row, and the second subscript refers to the column. You can pick out each individual number in your array when you do programming. So this is an important little idea, but again, don't get hung up on it, but it is an important little idea. Here's just an example. So you've got a matrix B. It is what it is there. The first thing you want to know is what's the dimension of B. So you look at B, you see it's got 2 rows, and it's got 3 columns, so it's a 2 by 3 matrix. Boom, boom. All right. Now, the next thing you want is a B22. So that's telling you to go to the second row and second column and read off the element there, and that's just 3. All right. So I don't think, I don't know, guys, I think even you will appreciate that, I can't ask you this in a midterm situation. Come on, it's just too easy, but it is what it is. The last one then is what's column 3? Column 3 is just 5 minus 2. And I've written the answer as a matrix itself, so I've just kind of cut up the matrix into columns, and I've just chosen the third column. And I've written it as a matrix because we're dealing with matrices, and it probably makes sense to write it as a matrix to be just consistent. All right. So again, this is what it is. The last, being, splicing up or cutting up a matrix into rows and columns. Sometimes you need to do that. When you guys get into third year, and I teach a thing called data analytics, and this is an important little idea: cutting up a matrix into rows and columns. All right, but the answer, I've written it as a matrix because we're dealing with matrices. So why not? Let's use the kind of matrix notation. Okay. Now, there are some special matrices, guys, that you need to get very happy with. And the first one are what are called row and column vectors. Now, if a matrix has a single row, it's called a row matrix or a row vector. All right, now this is very important, this word vector. Okay, so I will use this word vector pretty much to deal with matrices which have a single row, or usually actually it's a single column. So if a matrix is a single column, it's called a column matrix or a column vector, or usually just vector actually. So if I use the word vector, you should be thinking of a column matrix or a column vector, because columns are usually where the action is in matrix land. It's just the way it is. Row matrices are sometimes there, but they're not really where what we're interested in usually. We're usually in column matrices or vector matrices. That's what we're interested in. All right. The last one there is what's called the zero matrix. Now, the zero matrix is a matrix whose entries are all zero. And it's denoted by, and I didn't put this in, and I should have, the zero matrix is denoted by the number 0. And in print, it's boldface 0. And if you're writing it with a pen and paper, it's the number 0 with a line under it. And the dimensions of the zero matrix depend on the context of the question. What do I mean by that? I mean, you can tell what the dimensions of the zero matrix are by looking at all the other matrices in your analysis. They'll all be of one type, so that kind of tells you what the zero matrix is. But we'll come back to this. Well, I just want to introduce you to the concept of the zero matrix, because it is an important little concept, actually. It's a matrix whose entries are all 0. But the most important thing, guys, from this slide that I want you to take away is this idea of what a vector is. A vector is either a row matrix or more usually a column matrix. And it's very, very important. So, and usually, guys, if you have a vector matrix, it's usually denoted by a lowercase letter, actually, just convention. Because they are important and they occur quite a bit, they have got their own notation. So usually it's a boldface lowercase letter. This is the one exception. If you think back now, guys, I said, matrices are usually denoted by capital letters. If you have a vector, either a row vector or a column vector, it's usually denoted by a lowercase boldface letter in print, or a lowercase letter with a line under it if you're going to use a pen and paper. All right, so that's an important little idea. So these special matrices, guys, are where the action is in matrix land. If you live in matrix land, you're going to meet these every day. So this is important, this idea of what a vector of a vector in the context of matrices. Okay. Another very, very important idea is what's called a square matrix, because most matrices in engineering analysis, in fact, I would say 99.9% of matrices that you encounter are square matrices. And a square matrix has the same number of rows and columns. Now, I'll give some examples there. The first one, as I said, this is kind of the first one I shouldn't really give you really. It's a 1-by-1 matrix because it's got one row and one column, and it's not really a matrix, but sometimes it is. It's kind of a fluid thing, you know. We're all fluid in our own little way, and this matrix in particular is very fluid. All right. Sometimes you can consider it as a matrix. Sometimes you don't consider it as a matrix. And as I said, let's not consider it as a matrix. If you've just got a number on its own, it's not really a matrix, but sometimes it is. But I just put it in there for completeness. Where square matrices start really are 2-by-2, and then you've got 3-by-3, 4-by-4, 5-by-5. But typically in engineering analysis, it's a 3-by-3 matrix actually, or even a 4-by-4 matrix. But usually it's a 3-by-3 matrix because we live in a three-dimensional world. And so that's the reason why 3-by-3 matrices are the most important square matrix. But a 2-by-2 matrix is also very important as well. Okay, and they're very easy to identify. They have the same number of rows and columns, so you can see the structure. But it's a very important little idea, guys. Again, when I was starting off doing this thing, I was very dubious about what a square matrix is, and I wasn't very sure. But it's a very simple concept, really. It's the same number of rows and columns, and as I said to you, this is where typically engineering analysis resides. It uses square matrices all the time. And there are very special square matrices which you need to get happy with the terminology associated with them. Now, I've represented the matrices, the square matrices here, as a 3-by-3 matrix. As examples, using a 3-by-3 matrix in each case, because 3-by-3 matrices are the most important square matrices. But I could represent it as a 2-by-2 or a 4-by-4. It's exactly the same structure. Now, a diagonal matrix, folks, is a matrix that looks like a matrix underneath the words diagonal matrix, right? You've got zeros above what's called the main diagonal, A, B, C, and you've got zeros below the main diagonal. Now, the diagonal there, that diagonal going from top left to bottom right, is called the main diagonal. And the other diagonal that goes from top right to bottom left, it's not important, actually, because we write from left to right. And because we write from left to right, this main diagonal, the diagonal there containing the numbers A, B, and C, again, is where the action is. The other diagonal doesn't really come into things. So it's the kind of ignored diagonal. So this diagonal from top left to bottom right is called the main diagonal. And if you've got numbers in there in the main diagonal and you've got zeros everywhere else, you have what's called a diagonal matrix. There's a special diagonal matrix, which is called a scalar matrix, where you have all the entries in the main diagonal are the same. A represents some number. Okay, so you've got A. If you've got that kind of situation, you've got a scalar matrix. And there's a very important special case of a scalar matrix. It's really important, perhaps the most important matrix of them all. It's called the unit matrix, 1, 1, 1. And the unit matrix, and I haven't done it, and I should have, but I will come back to this. The unit matrix is usually represented as the capital letter I. All right, in text or in print, it's bold-faced capital I, and if you're using a pen and paper, it's capital I with a line underneath it. And again, guys, the unit matrix, the size of the unit matrix, the dimensions of the unit matrix depends on the context. You can tell what the dimensions of a unit matrix are by looking at all the other matrices in your analysis. Okay, sometimes the unit matrix will be a 2 by 2. Okay, so 2 by 2 unit matrix is 1, 0, 0, 1. But in this case, I've just represented it as a 3 by 3 because that's the most important of the analyses. If you stick with this stuff, if you stick with engineering analysis, this idea of upper triangular and lower triangular becomes very, very important, especially when you use what are called numerical methods to analyze engineering systems. Now, again, guys, loads of different words there. You don't have to know any of those words, but this is a very, very important. The upper triangular matrix is probably more important than the lower triangular matrix because, again, we write from left to right. So this is if in terms of triangular matrices, the upper ones are the good-looking ones, and the lower triangular matrix, unfortunately, are the not-so-good-looking ones. Okay, so we like the upper triangular matrices more than lower triangular matrices. Okay, and what is an upper triangular matrix? It's a matrix whose entries below the main diagonal are all 0. All right, and lower triangular matrix then is a triangular matrix, or is a matrix whose entries above the main diagonal are all 0s. But an upper triangular matrix, folks, is where the action is. So this is a very, very important little slide because I will be using this terminology as we go through this. So you need to know what I'm talking about, right? Diagonal matrix and especially unit matrix. We won't be using the upper triangular matrices and the lower triangular matrices very much in this course because, as I said, they're kind of associated with more advanced engineering analysis, but we're going to be just looking at maybe at the first 3, okay, and especially the last one there, the unit matrix, is a very, very important little idea. Okay, now matrices by themselves are okay, they're nice and you can touch them, you can look at them, but really we are interested in matrices because we can combine them. And it's the combination of things in mathematics that makes things interesting. Things by themselves are fine, but when you combine them together, that's where that kind of makes things much more interesting. It's like, I don't know, it's like characters in a novel, you know, or characters in a movie, because nobody reads anymore. But like if you have a movie about a single character, you know, there's only one person, it's not that interesting. Whereas if you've got 2 people in it in the movie, then it becomes much more interesting because you've got a combination of things, okay? And that's exactly the same with matrices. A matrix by itself is fine, but the only reason why we're interested in them is because we can combine them together. Sometimes, actually. Not always, but sometimes. Now, the simplest way of combining matrices is called what's called scalar multiplication. And what you do with scalar multiplication is you multiply a matrix by a number. Now, when you have numbers hanging around with matrices, numbers aren't called numbers, they're called scalars. I know it's just stupid terminology, but that's the way it is. And we combine scalars with matrices by just multiplying each element of the matrix by the scalar. Now, again, guys, this sounds very, very complicated. It's not at all complicated. Look, here's an example. A is a 2 by 2 matrix. It's a square matrix. No, it's not diagonal because the numbers off the main diagonal are not 0. But it's a square matrix. It's a 2 by 2 matrix. And you have to find 3 times A. So all you do, guys, is you multiply each of the elements of A by 3. And you write it down as a 2 by 2 matrix. Now you could argue, well, Jerry, you're not really combining matrices here. You're combining matrix by a number. But as I said, the numbers are kind of weird. Sometimes they're matrices, sometimes they're not. But let's just accept that this is one thing that you might want to do. And this is sometimes you do actually do this a lot, actually, multiplying matrices by scalars. Exactly like this. Okay? So you need to know what it is. So 3 times A is you just multiply each element of A by 3. Boom, boom. All right? Don't be put off by the stupid notation. And that's all this is. The reverse operation is actually very important as well. So you might have a matrix with a common factor, and you want to bring the factor outside the matrix because that makes the analysis simpler in many cases. And if you can do it, usually you do it because it does make the analysis that much easier. And why not? Life is about making things easier for yourself, right? So again, guys, this is no big deal. If you look at this matrix here, it's a 3 by 3 matrix. It's a square matrix. But each of the numbers there is even. So each of those numbers there is a multiple of 2. Now you might want to just bring the 2 outside and rewrite your matrix like this. Now guys, you don't have to do this if you don't want to. But usually people do this because it makes the next step, whatever the next step is, a little bit easier. Okay? So be prepared to do this. Now, as I say, it's not essential, and if you don't like doing this, you don't have to do it, but it does actually make things easier in many examples of engineering analysis. So why not do it? And so this is the kind of reverse of scalar multiplication. Okay, it's factoring out a common term. So why not do it? It just makes things nice. It makes things nicer. Okay, all right. Now, you can also add and subtract matrices. I need to warn you here, though, guys, that addition and subtraction, it's not that important. You can do it, and I'm going to do it now, and I'm going to define what it is. But I've never seen this done. Okay, I use matrices a bit in what I call research, but laughingly, really, because nobody cares. It's just, yeah. It's just, again, this is just, I don't know, I'm going to stop here because then it gets too sad. But I do a little bit of crappy research, and I use matrices a lot, actually. And I've never actually had to add and subtract matrices, but you can do it, provided the matrices have the same dimension. That's the key. That's important. If they have the same number of rows and the same number of columns, you can add and subtract them. If they don't, you walk away. You can't do it. That's just it. You just can't do it. And how do you do this? Well, you add and subtract corresponding elements. As you might think, really, if you had to come up with this yourself, this is what you might do. So here's the situation, right? You have 3 matrices here, A, B, and C. The first one's a 3 by 3. The second one is a 2 by 2. It's a square matrix, but it's not diagonal. If it was a diagonal matrix, it would be 1, 0, 0, 1, right? But it's not diagonal. And the last one then is 2 by 2 matrix. So the first question that first thing I'm asking you to do here is add A and B. All right. Now I might do this in the midterm or something similar. I'm not saying I will, but I might just to, have to come up with something. So, but in this case, guys, you can't add A and B because A is 3 by 3 and B is 2 by 2. You walk away. You can't do it. You can't calculate A plus B. By definition, the matrices have to have the same structure. Now you can, the next question that I'm asking you to do is subtract C from B. Now you can do that because B and C are 2 by 2 matrices. Boom, boom, so you can do that. And the way you do it, guys, is you write down the matrix B, write down the matrix C, and you subtract corresponding elements. So if you look at the 1, 1 element, it's 1 minus 2, and that's minus 1. And if you subtract the 1, 2 element, the 1, 2 elements, 0 minus 4 gives you minus 4, And then 1 minus minus 4. Be careful with this because minus by minus gives you plus. So you get 5 there in the 2, 1 entry. That's a 2, 1 entry. And the last one then is 1 minus 4, which is minus 3. So if you subtract two 2 by 2 matrices, you get a 2 by 2 matrix. Okay, you always get a matrix of the same dimension. Now, the last thing I'm asking you to do here, guys, is it looks difficult, but really it's just nonsense, right? It's just so easy. I'm asking you to multiply b by 3, c by 2, and add them. Okay, now remember what 3b means. It means you take b and you multiply each of the elements by 3. And that's what you get there. 2c means you take c and you multiply each of the elements by 2. And that's what you get there, 4, 8, minus 8, 8. And if I want to add two 2 by 2 matrices, I add the corresponding entries. So 3 plus 4 gives you 7. 0 plus 8 gives you 8. 3 plus minus 8 gives you minus 5. And 3 plus 8 gives you 11. Now, as I say, guys, very rarely do you come across this. It's not really very, very important. Okay? Unfortunately, because it's very simple, right? It's very easy. So it would be great if engineering analysis was about this, but it's not. Where the action is matrix multiplication. All right. Well, this is one of two very, very important areas, but this is probably 80% of engineering matrix operations involve multiplication. And as addition and subtraction, you can't always multiply matrices. All right. And actually, it's a lot more difficult to check if you can multiply matrices than it is to check if you can add and subtract. All right. So the next bullet point is really, really important. So here, hold on to your seats here. All right. Now, suppose you've got a matrix A and it has got dimensions m and n. So it's got m rows and n columns, whatever m is and whatever n is. And suppose you have a matrix B whose dimensions are s by t. So s is some number and t is some number. Now, if you want to multiply A by B, and the notation of that, folks, is you just write down the letter A, and beside it you write down the letter B. Okay, that's how you denote multiplication in matrices. Multiplication of matrices. You can only calculate AB if and only if the inner numbers, the second dimension of A is the same as the first dimension of B. All right, that's just the way it is. Okay, again now, guys, when I did this years ago, I had trouble with this, but it's true. Okay, you can only do multiplication if the second number of A is the same as the first number of B. If it is, then when you multiply A by B, you get a matrix whose dimensions are whatever the two numbers that are left. And in this case, the two dimensions that are left are m and t. All right? So that's a very, very important bullet point, guys. Multiplying A by B means you can only do it if n is equal to s. So the second dimension of A is the same as the first dimension of B. And if that is true, then what you get is you're going to, when you do the multiplication, you're going to get a matrix whose dimensions are the first dimension of A and the second dimension of B. So you're going to get an n by t. All right. And this, as I said, this is important, and this is kind of not obvious because in multiplication of numbers, guys, we do it all the time. 2 by 3 is 6, 3 by 2 is 6, 4 by 8 is 32. There's never an issue when you talk about numbers, but there is a big issue when you're talking about matrices. Now, typically in engineering analysis, it never happens that you have to worry about this because the engineering analysis is set up in such a way that you can always multiply. But sometimes it isn't, actually. All right. So here's the first step, folks. So here are four matrices, A, B, C, and D. And you will see, guys, the notation for A and B is different from the notation of C and D because A is a row vector and B is a column vector. So if you've got a vector, you write them usually as lowercase letters. C is a 2 by 2 and D is a 3 by 3. So they're proper matrices. So we use capital letters there. So I want to see if you can multiply AB, BC, CD, DA, AD, and CB. All right. I'm not going to actually do the multiplication, but I just want to check to see if I can do it first off before I actually do it. And I'll do it in the next lecture. So it's kind of a little bit of a cliffhanger here. Yeah. So you probably want to come back next time and see how you actually do it. Oh, it's so exciting. All right. So if you look at AB, folks, if I do that multiplication, The dimensions of A is a 1 by 3, and the dimensions of B is a 2 by 1 because it's 2 rows, 1 column. The numbers 3 and 2 are different, so I can't multiply AB, I walk away. Now, in the past, folks have asked us in the little midterms and maybe even in the final exam, you can't, this is an important little idea. So it is important to get on top of this, all right? If you look at BC, the dimensions of B are 2 by 1 because it's 2 rows, 1 column. C is a 2 by 2 square matrix. So if you look at the inner numbers there, folks, the 1 and the 2, they're different. All right? The 1 and the 2 are different, so you can't multiply BC. If you look at CD, again, you can't do it because C is a 2 by 2 and D is a 3 by 3. The numbers 2 and 3 are different. The inner two numbers there are different, so you can't do it. And similarly with DA, right? You can't do that either. D is a 3 by 3 and A is a 1 by 3. The numbers 3 and 1 are different. You can't multiply. So what can you do? Well, you can do this. You can multiply A by D because A is a 1 by 3 and D is a 3 by 3 matrix. And you will see that the innermost numbers there, 3 and 3, are the same. So when you multiply A by D, you get what's the outer two numbers. You're going to get a matrix whose dimensions are 1 and 3. All right. So when you multiply AD, you're going to get 1 row and 3 columns. And I'll show you how to do that next week. No, in the next lecture, actually, this week. If you multiply CB, folks, C is a 2 by 2 and B is a 2 by 1. So you're going to get a 2 by 1 matrix. And that multiplication there, CB, kind of is a very important idea. Multiplying a 2 by 2 matrix by a vector is really, really important to get another vector. It's really, really important. That's really what matrix multiplication is all about, the last one there. And I'll show you how to do it next week. No, not next week. This week. It's even more exciting. Okay, guys, and I'm going to end it there. And there's another lecture on its way. And enjoy.